All right, so we left off, we've been dealing with confidence intervals, so we'll keep doing that today. And just to have this as a, excuse me, reference. Also, I apologize. I think my allergies are really kicking my ass today. So my voice might be a little raspy, but we left off talking about this confidence interval, what we were building for a true population proportion. All we could see was our sample proportion. So what we were doing was really, we would be given the sample size, our sample proportion we can calculate. I think that's where we left off in Excel. We said we can calculate from a 1-0 variable. If we simply take the mean, that's our sample proportion. The sample proportion is just a unique example of the sample mean, and that's when we have a 1-0 variable. So the only thing left that we really need to do was find this Z value such that the area on either side, right, or the area in our tails was alpha, which meant we had half of alpha in each tail. Right? So that was kind of the setup. So if we go to Excel, and this is not the file, I want the file that we were working off of last class, which I'm going to delete all of this because this is what we need to build. We had done that for a sample mean, but we had this 1-0 variable, which was more likes and dislikes. And we found the mean of that variable, which the mean of a 1-0 variable just represents my sample proportion. So you can think about here, my sample proportion, if you want like another word for it, this is P hat, right? So if it helps you to remember, that was our P hat. We could also find our sample size. Now we already found it last class, just to, remember how we were doing this. That was simply using that count function. All the count function does is if you select a variable, so Command Shift on a Mac, hit the down arrow, then hit enter, it'll kind of close the parenthesis for you. And that count function just counts the number of cells that have data in it, right? So that will give us the number of observations. So we're going to set this up exactly like we did for our sample mean. We're going to have the 90, 95, and 99% confidence levels, which we know that corresponds to alphas of what? So my alpha for the 90% confidence interval would be 0.1, for 95, 0.05, and 99.01. The same thing that we had for those sample means up there. And I think I added these in just to show you we could do it for more, but we're just going to use the benchmark values. Okay. So the first thing we just said, we can break this up into steps, right? So the first thing I'm going to do is find these Z values. So we can do it one of two ways. The first way is we can just look up that area in the tail that we want, which is alpha over 2. So anytime we know the area or the probability of that tail, and we want to find the corresponding Z score, we said we're working in the inverse, right? So norm.s.inv says we're using a standard normal distribution, Z values, and we want the area in the tail to be alpha divided by 2. Now, what was the issue? We said if we just look up alpha over 2, we're going to get that negative number of standard deviations we need to go. But the positive and negative sign are already built into our confidence interval equation. So we just want the absolute value. So we go to the beginning of this and say, okay, just take the absolute value of whatever that Z value is, right? Whatever Z value that norm.s.inv function gives me. Okay. Any questions on that? This is really the exact same thing that we did. If we go up here to that the sample mean, it's the exact same thing that we did. Okay? Now we said there was an alternative way to do this, which is why I had this additional column. We don't have to do it here. I had already showed, but we could have done 1 minus alpha over 2, and then not had to worry about taking the absolute value, because if we want alpha over 2 in the upper right tail, that gives us the Z value but positive. However, that norm.s.inv function always looks at the area to the left. So the area to the left of this Z value would just be 1 minus alpha over 2. So either way is correct. Either way gives us the right answer. But here, we only have to use one of them. Okay? Now, if I copy this down, it gives me the number of standard deviations away I need to go for the next 2 levels of confidence that I also want to build confidence intervals for. So we'll end up with 3 different confidence intervals. each for a different level of confidence. Okay. Any questions up to this point? Yeah, so I had this in here. When I copy this down, if I just drag it down, so just left click and drag this down, it'll then update the cell reference to use the next alpha. Right? Yep. Any questions on that? Okay. So I'm going to break this down into steps, and I'm going to calculate that standard deviation of my sample proportions in a cell up here. So I'm just going to put this up here, and it will make my life a little bit easier. I'll show you why. So we did that the same kind of thing with the sample means, but here the standard deviation of my sample proportions is the square root of my sample proportion times 1 minus my sample proportion, and then divided by my sample size. Okay. So all I'm doing there is using Excel to be my calculator. I'm just kind of breaking things up into steps. So then once I have this value, I just have to plug in one number here. Okay. So I've got my sample proportion, I've got my Z values, and I'll now have my standard deviation of my sample proportions. Now it's just using Excel to do some pretty simple calculations for me. Okay. So once I have that, I can find my lower and my upper bounds. Okay. So what is my lower bound? Well, it's just take my sample proportion, so that's over here, subtract the number of standard deviations away I need to go, or that Z value that gives me alpha over 2 on either side of my confidence interval. If that's the number of standard deviations away I go, I'll then multiply that by whatever the standard deviation actually is. So I'm just using Excel to do some simple calculations for me, right? I've calculated each one of these values. Now it's just a matter of kind of getting them plugged in, so to speak. Right? So that's easy enough, but what if I want to copy this down and find a lower bound for my next 2 confidence levels? Well, what's the only thing that changes when we're doing a different confidence level? My sample proportion is going to be the same. My sample sizes are the same. The only thing that changes is that alpha, which then changes what Z value I need to use. So when I copy this down, the only cell reference I want to update is this Z value cell reference, or the red one, right? So everything else, I'm going to freeze those cell references. So now when I copy this down, the only thing that updates is that Z value. Questions there? Keep moving. So now when I copy this down, I should get my lower bounds for the next 2 confidence levels that I wanted to build. We also said last class, if I double click here, I highlight my formula, I copy it, hit enter to get out of the cell, I go over here and paste it. I have the exact same formula for my upper bound, but I need to change that negative to a positive, right? I'm adding my margin of error there. Right? So I'm just changing that one sign. That's the only difference to our upper and lower bound equations. When I copy and paste it that way, none of the cell references update. If I dragged it over, well, now my cell reference, so I can kind of show you, if I just drag this over, notice, oh, I'm not using my Z value now. It's using my lower bound. That's not what I wanted to do, right? So the other process, by copying and pasting it and just changing the negative to a plus sign, I didn't have to worry about that cell reference updating. Excuse me. Any questions on that? And also doing it this way, it kept my other cells frozen. So I just have to copy this down, keeps those the same, and just updates the Z value it's using. Yeah. Here? Yeah. Yep. So you should just be using that built-in average function. And then just selecting, yep. Make sure you don't select the label if it's giving you a different value or something, an error. Okay. Question, other questions? I guess I should maybe move this. Any other questions? I want to see a cell again. Or... So very similar. I mean, really, really similar to what we did last class for the sample mean. It's just that our standard deviation calculation is a little bit different. And when we find the sample mean, it's actually a sample proportion when we're finding the mean of a 1-0 variable. Any other questions there? Know that? Oh, I actually want to point this out. So let's say that if we think about, it doesn't matter if we're using the sample proportion or we're doing a sample mean, or this is what. If I have the same levels of confidence, I'm going to have to go out the same number of standard deviations. So maybe I need to go out like 2.5 standard deviations. But the width of my confidence interval is really dictated by the standard deviation of my sample statistic, whether that's a sample proportion or a sample mean, right? Because going 2.5 standard deviations away, well, that's going to be a different amount if the standard deviation is 10 or it's 1,000, right? So if I looked at, oops, sorry. A little bit off the screen there. So if I looked at these standard deviation of my sample mean here, it's like 4,700. So if I go, 2.5 approximately standard deviations away, the width of my confidence interval here is like 23,000, 24,000-ish, right? Because 2.5 standard deviations is a pretty big number. But for my sample proportions, think about it, we can only ever see them between 0 and 1. So we're likely going to get a much more narrow range of possible values, which sure enough, the standard deviation of my sample proportions here is 0.003. So going 2.5 standard deviations to the left and right is not going very far at all, right? 0.003 times 2.5 is a very small number. Here are intervals. I mean, these are what, 0.012 maybe in width. So really, that standard deviation of our sample statistic is what dictates how big our interval is. So you'll notice if we have really large sample sizes, what's going to happen to that standard deviation? Well, if the denominator is larger, it's going to go down. Right? So when we have pretty large sample sizes, we might end up with really low standard deviations for our sample statistic, which means that our margin of error is small, which means we get a pretty narrow confidence interval, which is a good thing because I'm able to like pinpoint down. I'm telling you with 99% confidence, the true population proportion is in between what, 0.78 and 0.799. That's a pretty narrow range. Now, if I had a smaller sample size, so let's say my sample size is relatively, goes down. Well, that would actually make the denominator smaller. So it would make my standard deviation larger. Margin of error is larger, I should get a wider interval. So we can actually test that. Let's say I found the exact same sample proportion, but I only had a data set that was 120 observations, so quite a bit smaller. So what should happen with a smaller sample size is that would drive up the standard deviation, which makes my margin of error larger, which kind of gives me this wider interval. So sure enough, my standard deviation would go up to about 0.037. My confidence intervals here now have a width of, instead of 0.012, have a width of about 0.12, right? So a much wider range of possible values. Okay. Hope that's not locked. But that wasn't my sample size. My sample size was much larger, and so that's why we're getting these much narrower confidence intervals there. Okay. Much more narrow. Any questions on anything here that we did? You want to see a cell again, or okay with this for now? All right, so I will get this posted up on Canvas so that you kind of have the completed version with both of what we did on Wednesday and on Monday, or sorry, and on today. On Monday, we got one more type of example that we need to look at in Excel. So I'm going to push that Excel due date up to be at the end of the day next Friday. So you get a few more days, all next week to kind of work on finishing that Excel assignment. After today, you should be able to get through everything except for the last problem. And we'll cover that on Monday. Although it's going to look really similar to what we did here. with just a little tweak, okay, just a little bit of a tweak to it. So honestly, you could probably maybe almost figure it out on your own if you really wanted to complete the whole thing, but we'll cover it on Monday for sure, okay? I'll also be posting it when I get back to my office after class, a smart book assignment. So it's going to be over hypothesis testing. That'll be due before we start class on Monday. So you could go through it this afternoon, tomorrow, Sunday, before class on Monday. Should take 10 minutes, just kind of prime you for the material that we're about to cover next week, which is hypothesis testing. Okay? So we'll start hypothesis testing on Monday. So just wanted to kind of mention all of that there before I forgot, or so I don't forget before the end of class. Questions before we go back to the slides here real quick? Okay. So here's some reference slides for the, oh, actually, that's not what they are. There they are. Here's some reference slides for what we did in Excel. And then actually, I forgot to put these up here. So let me do this real quick. I think I put them up for the other section before we started, and I forgot to do it for this one. All right, so let's go here, files. I added some slides in to what we had at the beginning of the week. Got through a little bit more than I was expecting, which is a good thing. So I just replaced those. So there should be the same slides that we had earlier in the week, but with a couple more added in. So here's kind of the start of the new slides that I added in. So this should be right after the conference interval stuff. And honestly, I'll be doing a lot of this on the dot cam, so we don't have to worry too much about these slides. So let's see what's here. So, we started out with these examples where we didn't know the population mean, but we somehow had the population variance. And we said, yeah, this is kind of weird, not very practical. More often than not, we're not going to have a known population variance if we don't know the population mean. So it's a good question. What do? We basically just calculate a sample variance from our sample, and then we use that instead of a population variance. So now the standard deviation of our sample means, we're going to write it with an S instead of a sigma to just denote we calculated the standard deviation of our sample means using a sample variance, not a known population variance. So we usually call these types of examples, we have an unknown population variance. So all we can do is the next best thing, which is to use our sample variance. So if we do that, we'll think about what we were doing before. To calculate Z values, when I was using the standard deviation of my sample means where I had a known population variance, right? So this created Z values, which we knew were standard normally distributed. So we could then use that standard normal distribution table. The problem is, if we do this when we only have a standard deviation on our sample means, where we had to use a sample variance, not a known population variance, is that this doesn't actually give us a value, or doesn't give us values that are standard normally distributed. So this doesn't give me a Z value. It actually gives us what we call a T value. It still represents the number of standard deviations away from the mean I am, but it's not standard normally distributed. So remember, our Z values were normally distributed with a mean 0 variance of 1. So that was our standard normal distribution. Because we're dividing by this standard deviation of our sample means where we used a sample variance, if we remember when we calculate a sample variance, it was like this. We divided by n-1 when we only had a sample data, right? We were calculating a sample variance. So because we're dividing by n-1, that's always going to overinflate our sample variance a little bit, which is going to overinflate kind of this standard deviation of our sample means. And so when we divide by this standard deviation that uses a sample variance, it doesn't give us a Z value. It gives us a student T distribution value. And the student T distribution will still be normally distributed with a mean of 0, but its variance is going to be a little bit larger than 1 now because we were dividing by that n-1. So we know now that if we only have a sample variance, when we turn these into the number of standard deviations away, it's going to follow a student T distribution where the variance is a little bit higher than 1. Okay. So this presents some problems for us, right? But I think, let's make sure I hit all those properties here. So it's, oh, I didn't. Let me show you visually this. So you can imagine, let's say like my sample size was 2. Well, then when I'm dividing by 2 minus 1 will be 1. Dividing by 2 instead of 1 would create a pretty big difference in the variance that I get. Whereas if I had 1,000 and I divide by 999, that's not going to cause near as much of a difference. And so every single different sample size will have a slightly different variance on its t-values. So we're actually going to have a student t-distribution at every single sample size. So it's not just one student t-distribution, it's a different student t-distribution at every single sample size. Right? As the sample size gets larger, that variance is going to get closer and closer to 1. Right? Because dividing by 1,000 instead of 999 instead of 1,000 isn't near as big of a deal as dividing by 1 instead of 2. So as that sample size gets larger, it's going to like decrease that variance, getting closer and closer to that value of 1, which is the standard normal distribution. Okay? So as we have really high sample sizes, we can actually use the standard normal distribution as an approximation for the student t. And usually we say anything over 1,000. And I'll bring this back up again here in a second. So we've got a family of distributions, very similar to standard normal. We said the variance is a little bit higher than 1, so they're going to be more spread out than our standard normal. And it might seem a little goofy for now, but kind of getting this terminology out of the way, we're going to use it for some things down the road. We're going to identify the student t distribution that we're using, not based off of the sample size, but based off of degrees of freedom. So it's going to seem stupid now because, well, why not based off the sample size? Because all the degrees of freedom is your sample size minus 1. Okay. So this is the reason why it's pretty simplistic now is because what the degrees of freedom refers to is we used one sample statistic to calculate another. So we use our sample mean to calculate our sample variance, which was then used in determining what this t-value was. So you subtract 1. We use one sample statistic to calculate another, so n minus 1. There's other statistics that we won't deal with in this class, but you might use like, I think, let's see, I remember off the top of my head. But there's like, if you do, well, what's one that we could think about? There's something called ANOVA testing, which is like you do analysis of variance. So you're using multiple sample variances to calculate this other thing. And so because you're using multiple sample statistics, you have degrees of freedom, sometimes like n minus 3, n minus 4. We don't have to worry about that yet. We're doing a very simple one. It's simply n minus 1. Okay. And that's going to identify what student t distribution that we need to use. Okay. I also mentioned it's symmetric, I think, or at least I made the point that it's still centered around that mean of 0. So it's just like a normal distribution, the student t distributions are symmetric. They are going to be a little more spread out, which we already mentioned, right? That variance is larger than 1. And then as we get to higher and higher sample sizes, it converges to a standard normal. So I said 100 here. On most of the examples I give you, you're not going to see anything between 0 and 1,000, or 0, between 100 and 1,000. We'll typically be dealing with sample sizes that are less than 100 or greater than 1,000. Because the in-between, it gets kind of iffy, like, is it a close enough approximation? Well, it depends on how close you want your approximation to be. Anything over 1,000, we're definitely going to be close enough to use the standard normal to approximate the student t. Anything less than 100, we can't. We have to use that student t distribution. Okay. So I want to give a little bit of insight. The next slide's okay, but I think I can do a better job. So just using the .cam stuff. So let's go. I'm going to put the student t and the standard normal distribution on the same graph. So here's my standard normal distribution. We know that its mean is 0 and its variance is 1. Okay. What do we know about the student t distribution? Well, it's still centered around 0 and symmetric around 0. But its variance, doesn't matter what degrees of freedom we have, the variance of our student t will always be greater than 1, right? It's a little bit more spread out. So if it has a higher variance, what is true about the values close to the mean? Is it more or less likely we'll see those values? Yeah, if it's more spread out, it means that it's less likely we see values near the mean, more likely we see values further from the mean. So our distribution is going to be flatter. Okay? Now I've drawn this pretty extreme. I doubt it gets that much flatter, but I think this helps kind of with the next visual. So here, this red was our kind of student t distribution. This black line here represented our standard normal. Okay? So when we're doing things like building confidence intervals, and we say, well, look, there's a certain z value that gives me maybe 0.025 in that right tail. Okay? We looked that up. I think the z value is 1.96, gives you 0.025 in that tail under the curve to the right of that z value. Now, if we keep using the same values that we were before to build confidence intervals when we only have a sample variance, well, if I keep using 1.96, notice the area under the curve to the right of that, much larger than 0.025 now. So if I want to get 0.025 under the curve in that tail for a student t distribution, I'm going to have to use a t value that's much larger. So when we're doing confidence intervals for where that true population mean is, when we only have a sample variance, our student t values are going to be a little bit different than what we were using when we had a standard normal distribution. Okay. And I tried to give another visual here on this slide. I don't like it as much just because I don't have the area under the curve shaded. But you can imagine if this black line is my standard normal distribution, the area under that black curve is 0.025. But if I look at the area to the right of 1.96 under these blue and green curves, well, that's much, you can kind of see it's going to be a much larger area. In fact, we can find what those areas are. And the way that you can do this is the student t distribution is still a normally distributed variable. So you still have that probability mass function, you can still integrate it. We don't want to do the integration. Someone's already done it for us. So under the Files tab, I put a student t distribution table. So the one that should be up there, let's just double check that. At t tables, right? I guess I probably should say t table. But if I open that up, it's going to work a little bit differently than the standard normal distribution table. So the standard normal distribution always looks at the area to the left. The student t distribution table actually looks at the upper right tail, which is kind of nice because then everything's positive. I don't have to worry about like absolute values when I'm looking these up. So the way that this table works is that it's always thinking about the area in that upper right tail. To not cause any confusion, because sometimes like we're looking up alpha over 2, I'm going to repost this table to make it easier. I'm going to just like put a text box or something over this. This alpha doesn't necessarily correspond to the alpha that we're using in our problems. This is just, they happen to use the same Greek letter to represent the area in this upper right tail. So I'm just going to cross these out or get rid of them. You can just think about, we're looking at this area in the upper right tail. Okay. So these column headings represent the area in that upper right tail. Okay. So for instance, when I was thinking about, I wanted 0.025 in my upper right tail, but I wasn't dealing with a standard normal distribution. Let's say that, excuse me, so we've got, let's say we were building a confidence interval for the 95% confidence level. Alpha is 0.05. So half of alpha, or the area in each tail, alpha over 2, would be, divided by 2. Alpha over 2 is 0.05 over 2, which is 0.025. Okay. So I want to find the t value that gives me 0.025 in the upper right tail. And let's say my sample size is 20, which means my degrees of freedom, n minus 1, is 20 minus 1, or 19. Okay. So I know the area until I want is 0.025. My degrees of freedom that I wanted is 19. So I'll go to this table. I find the area I want in the upper right tail, 0.025. And then I just scroll down to my degrees of freedom, 19. So the t-value that would give me that area in the tail of 0.025 at the degrees of freedom of 19 is 2.093. So notice it's a little bit higher than that 1.96 that we were using from the standard normal distribution. Okay. Any questions about how I was using that table? So you'll find the area that you want in the tail. That's your column heading. You then need to go down to whatever your degrees of freedom is. And these numbers in the middle now represent these t-values, or the number of standard deviations away. Okay. So it's kind of the exact opposite of the standard normal table, where our row and column headings were the z-values and the numbers in the middle were probabilities. Now the probabilities in the tail are up here as my column heading, and the t-values are actually what's here in the middle. Okay. So it's almost like they're the exact opposite. Questions there before we keep moving? So now we know how to use the student t-table a little bit. I said that as the sample size or as the degrees of freedom gets larger, we start to get approaching that standard normal distribution. So here for that area of 0.025, the standard normal value, the z-value that gives me that area in that upper right tail, would be 1.96. So as I get higher and higher degrees of freedom, these t-values that give me that desired 0.025 for the tail should be getting closer and closer to that 1.96. So I keep scrolling down, and sure enough, it looks like they're getting closer, or they're getting smaller. The end of this table, so there's two sides to it. There's just a lot of different sample sizes we need to know. Notice they start making big jumps here at the end instead of going up by 1. So at 100, that t-value is 1.984. So is that a close enough approximation to 1.96? I don't know. It's kind of close, but it's still a little bit off. But notice by the time we get to degrees of freedom of 1,000, 1.962, we're only off of the third decimal. We're only off by 0.002. So probably by the time we get to 1,000, it's okay to use that standard normal distribution as an approximation for our student t. Now, most of the examples I give you, like I said, we're going to have sample size under 100. If we had sample sizes over 1,000, we could use the standard normal to approximate. Okay. In fact, if I could get a degrees of freedom of infinity, notice that's the exact value I would find for my standard normal. So the last row of this student t table actually has the standard normal distribution values. So it's almost like two tables in one. I actually think when you're doing confidence intervals, it's easier to use this last row of the student t table to find your standard normal values. Like let's say you're doing a proportion example. Well, we use the standard normal distribution there. I could just get those z values from the last row of my student t table. So it's kind of a nice shortcut. And not only can I get them from that last row, I'm not constrained to 2 decimals. It gives me what those values are out to the third decimal. So usually, I think this is 0.005 in the tail. That would usually be a z value of 2.57 or in between 2.57, 2.58. So there we had to use the higher of the two. I don't have to do that if I use this last row to get the value. It gives it to me out to the third decimal, 2.576. Right? It was in between those two, but this gives it to me out to the third decimal. So I'll start using this last row as kind of a shortcut instead of using the standard normal, hunting down where that probability is. I personally think it's just a lot easier when we're doing these confidence intervals. Find the area in the tail that we want. If it's a standard normal distribution example, go to this last row. It's got the values there for you. But otherwise, all the other degrees of freedom for our student t, we can use the rows above that. So that's kind of a helpful thing about that student t. And this is also think about like, this is kind of theoretical. Like we can never truly have an infinite sample size. I don't know, it's probably go on like a tangent about like infinity minus 1 is smaller than infinity. So like there's different sizes of infinity and we can like go down this whole thing. But the idea of this last row is if we could get to that infinite degrees of freedom, that would be a standard normal distribution, right? It wouldn't even be an approximation at that point. So we can use that last row when we're doing other examples where we're not having to use a student t as well. Okay. So I have that kind of as a reminder here on this slide that last row is kind of useful for us as well. So here is, our confidence interval equation when we only have a sample variance. It's going to be constructed really the same way as what we were doing before. It's just that instead of a z value that gives us alpha over 2 on each side, we now have to look up a t value. Now, it still represents the number of standard deviations away that we need to go. It just accounts for the fact that we're only using a sample variance to calculate that standard deviation of our sample means. Okay. Once I plug the numbers in, though, it looks like exactly like the other examples we were doing when we had a known population variance. But prior to the numbers getting plugged in, the only thing that's really changed is I need to use that student t distribution now. And if I do this intermediate calculation to find my standard deviation of my sample means, I'm using a sample variance instead of a population, known population variance. Okay. Any questions on this? So where are we at in time? Oops. Okay, we'll make it out a little bit early here. So I already mentioned those homeworks, extending the Excel, because on Monday, we'll pick up and where right here, we'll go a couple examples where we only have a sample variance using that student t distribution table. We'll then look and see how we do it in Excel. It's going to be very much like how we did confidence intervals for population means when we had a known population variance. It's only going to be a couple things that get tweaked. So the general setup and everything is exactly the same. We're just going to have to, instead of being able to use norm.s.inv functions, that was using the standard normal, we're going to have to use functions that are built in for the student t distribution. So instead of norm.s.inv, we're going to start using something called the t.inv function. So I'll show you how we use that. Like I said, you could probably almost figure it out on your own just from that limited information I just gave you. But we'll do that for like the first half of class, and we'll do hypothesis testing in the second half. Okay. I do have one more thing that I want to show you before we get out of here today. So we'll take a little 5-10 minutes here. But I think it'll help maybe solidify kind of what we're doing with confidence intervals. So if you remember when I first introduced the idea of confidence, and this is up on Canvas under the in-class data folder, you don't need to open it. Everything's already filled out, but I just want to show some things to you to hopefully make confidence intervals make a little more sense. So remember when I introduced it and I said, okay, if we saw a sample mean here, we build a confidence interval, it includes the population mean, we see a sample mean over here, and we built one and we include it. But if we see one way out here, that confidence interval would include it. So the idea was that when we say things with 90% confidence, that means that if I were able to just continuously take sample after sample and build confidence intervals for all of those samples, 90% of the time, those confidence intervals include the population mean. 10% of the time they wouldn't. All right. So I can actually try to prove this to myself. So I'm going to set the alpha to be 0.1. So I've got 90% confidence intervals. I've got samples of size 50, and I took 1,000 random samples. So notice here, I've got 1,000 different columns, which represent 1,000 different random samples that I took from some population data. So I have the population data and I have sample data all in one. I'm kind of cheating here. Right? Because I have the population data. I didn't need to take a sample, but to prove this to myself, I did. So here I've got every different student I've had in business stats, I think except for the fall. I had their letter grade. I took their names off of it and just gave them wasn't really their student ID number, but it's like I just 1, 2, 3, 4, 5, all the way to the last student. Okay. So I have 431 students, just use that count function. I found the population mean, and I could find my population variance. Okay. Now, I did some stuff here that I would never expect you guys to do, but it does show kind of the power of Excel. So there's something in Excel called VLOOKUP. We can use this random number generator, which randomly generates a number. Using this VLOOKUP, it then goes to column A, and it finds that student. So maybe it generates the number 59. So it goes to that 59th student, sees that their exam score was 77, and then it would put that 77 into the cell, right? So every one of these cells generates a different random number, right? And you can ignore this first column. It's just something about the random number generator, so that I was making sure I was getting a different sample every single time. But I basically now have 1,000 samples with 50 random observations in them. I can find the sample mean, right? Once I have the sample mean, I've got the sample size of 50. I've got a known population variance up here, and my alpha is 0.1. Well, that's everything I needed to build confidence intervals. So instead of doing it in steps, I calculated the lower bound. All right, I've found that z value for alpha over 2. I took the square root of the population variance over my sample size. I built it, I subtracted my margin of error from my sample mean. I did the same thing for my upper bound, but I added my margin of error. Basically here, I've created upper and lower bounds for every single one of these samples. Well, now what I can do is say, well, look, this first sample, 78 to 85, does that include the true population mean of 79.8? Sure, it falls in that range. So I'll put a 1 in this cell. I'll then do that for every single sample. Now, let's see if we can find one here. So this one was 71.4 to 78.2. So that population mean, which I think was like 79 point something, is not in that confidence interval, right? So that got a 0. So I basically was just identifying 1, if the population mean was within the confidence interval for that sample, 0 if not. Now, I used some kind of if statements here that we haven't really went over, but we will eventually use these. And really the general idea is I'm just going to check to see if something's true. If it is true, I want to put a certain value into this cell. If it's not true, I want to put another value, right? So here I say, okay, look at this and say, if this population mean in E1 is less than my upper bound, then check to see if this is also true. Is my population mean greater than the lower bound? So that's really just telling me, is it somewhere in this confidence? Is it, does it fall within my population mean? Does it fall within my confidence interval? If that's true, put a 1. If either of those aren't true, that would mean it's outside my interval, put a 0. So I've got identified for all these different samples, whether or not, once I found the sample mean, built these confidence intervals, did it include the true population mean? I then added all these up by just using that sum function. So like, for instance, I could just go equals sum, control shift, hit the over, hit enter. It's pretty easy to do that. So this counts the number of times that the confidence interval included the population mean. I've got 1,000 different samples. So I just took the number of times my confidence interval included the population mean, divided by 1,000. That would tell me the proportion of times that my confidence intervals included the population mean, and then multiply it by 100 just to make it easier to talk in percentages. So here, notice every time I hit enter, it randomly generates new numbers. So I'm constantly getting new samples here. But notice the percent of times when I'm using that alpha of 0.1, that corresponds to 90% confidence. Notice 90.4% of the time, the sample that I had, and when I calculated the confidence interval, that confidence interval included the population mean. And if I click here and randomly generate some new numbers, notice it gets a little bit higher, sometimes a little bit lower, but it's always floating right around that 90%, right? Now it's not perfectly 90, and it floats a little bit around it because I've only got 1,000 samples. This would be even more precise if I did 10,000 different samples, right? Or 100,000 would be even more precise. Okay. And I can go and prove this to myself. It doesn't matter what alpha is. So if I choose alpha to be 0.01, that should be the 99% confidence level. So now when I count up the number of samples that had a confidence interval that included the population mean, hopefully I'm getting about 99% of them did. Sure enough, 99.1, 98.9, always floating right there around whatever that confidence level was. Okay. So sometimes the math will get bogged down too much. Conceptually, sometimes something like this, seeing it with the data makes it make a little more sense. If I was actually able to do, take 1,000 different samples, when I build these confidence intervals, whatever confidence level I'm building them at, that's the percent of the time that I'm actually capturing that population mean within my interval. Okay. Any questions on that or anything that we went over? So we'll pick back up. We'll finish confidence intervals on Monday. We'll then kind of go into hypothesis testing on Monday as well, which will be the last thing that we have before the exam, which is not next week, but the following Wednesday. Okay. All right. Have a fun, safe weekend. I will see you guys on Monday.